So addition theorem of a probability. Addition theorem. So it's if suppose we have two events, event A and event B. Occurrence of at least any one of these two events, so that we can say union of events, at least any one from these two events. Okay, so that we call it as what? Addition theorem. Suppose sample space has 1 2 3 4 5 6, then event A has 2 4 6 and event B has 3 6. Now addition theorem means, already we learned, union of probabilities. So A union B is equal to 2 3 4 6. Occurrence of any one of this, we say union of these two. Now when it comes to the probability, so calculating separately, first union of your probability of event A. How many favorable cases are there here? 2 4 6, 3 favorable cases are there. So M or N of favorable cases, event A is 3, N of S is equal to 6. Then probability of A is equal to 3 divided by 6. Then probability of B. So how many cases are there here? Favorable cases to event B. So N of B is equal to 2. Then probability of B is equal to 2 divided by 6. So probability of getting event A is 3 by 6. Probability of getting event B is 2 by 6. Now at least one from the both event. So it's a, we can say union, but addition. But we should know one thing here. In both the event, is there any common event? So here in event A, 2 4 6, 3 elements are there, and in B 3 6, and in both 6 is a common. In both cases 6 is a common factor. Okay, now if we add directly, when we have written here A union B, so we have written 6 only one time. So here favorable cases of event A union B is N of A union B is equal to 1 2 3 4. So favorable cases to event A are 3 and favorable cases to event B are 2. If you put them together, so here 3, here 2 means 5 cases should be there. But here only 4 cases are there, because repetitive elements we take only one time. So 6 6 here only written one time, because 2 times it will not occur. When we are throwing a die, only one time. Okay, if 6 appears, so it is assumed that event A and event B both happened simultaneously. Okay, so if it appears once, we say event A has occurred, then we go for second throw. No. So in one throw itself, if 6 appears, we say that both occurred. If apart from 6 any other number comes, say 2 comes, so at least either A or B, so in that A has occurred. So A union B means, so this event has occurred. So probability of getting at least any one from event A and event B is 4 divided by 6, but not 3 plus 2, 5 divided by 6. So probability of getting event A union B, or at least of probability of A and probability of B, is not 5 by 6, it is 4 by 6. Why that happens? So because here we should see here whether the both events are mutually exclusive or not, and all the events are equally likely or not. So here all the events, all the outcomes are equally likely, but they are not mutually exclusive. So when they both are mutually exclusive, then union, that is P of A plus P of B, is equal to P of A union B. So here A union B is equal to A plus B. But here, as there is a common factor between both, it will not occur two times, only one time. Okay, so favorable cases to A union B is 4, not 5. Why? Because of common factor 6 here. Okay, so here how to arrive to this answer directly without going for this event A union B here. So that the formula given by addition theorem in the probability chapter. So here if it is suppose instead of 6 here, now 2, 4, 6 is event A, 3 and 5 is event B. Then probability of getting A is 3 by 6 and probability of getting B is 2 by 6. Probability of getting any of these, at least one of these, that is A union B, is equal to 2, 3, 4, 5, 6. That is 1, 2, 3, 4, 5. 5 outcomes. So 5 by 6. 3 by 6 plus 2 by 6. That is 5 by 6. So here, when there are mutually exclusive events, then addition theorem, probability of A union B is equal to P of A plus P of B. If they are not mutually exclusive, then probability of A union B or A plus B is equal to P of A plus P of B. They are not mutually exclusive, means there will be a common factor between two events. Okay, so that common factor will not repeat. So if we count them all, so it shows lesser probability. So what we do, we deduct that common factor here, which is repetitive in nature. So minus probability of P of A intersection B. P of A union B is equal to P of A plus B of B minus P of A intersection B. When the events are not mutually exclusive. If the events are mutually exclusive, P of A plus B of B. Example, event A is 3 by 6, event B is 2 by 6. So P of A plus P of B is 5 by 6. Okay, now I will go back to the earlier example, that is event A is 2, 4, 6, event B is 3 and 6. So there is a common factor 6 between both here. So A union B is equal to 2, 4, 2, 3, 4, 6. So 6 common has taken only one time. Means here which is left? A intersection B, that is 6. The common factor between both is left here. So P of A, probability of getting event A is equal to 2, 4, 6, that is 3, 3 by 6, and P of B is 3, 6, so getting probability of B is 2 by 6, and probability of getting at least one of these two will be given by this formula. P of A union B, or P of A plus B, or P of A or B is equal to P of A plus P of B minus P of A intersection B. Just cross check it. P of A for this example is 3 by 6 plus P of B for this example is 2 by 6 minus P of A intersection B, that is this one. So probability of getting A intersection B, okay, common, which is common between both, okay. So that is only one factor is there, so 1 by 6. So here minus 1 divided by 6. So denominator is the same for all the probabilities here. So calculate directly. 3 plus 2, 5. 5 minus 1 is 4. So 4 by 6. Probability of getting at least A or B event is 4 by 6. And even if we prepare separate here, then also 1, 2, 3, 4. So 4 by 6. So instead of writing union of both, or for few calculation we cannot write even here, okay. So therefore we go for this addition theorem formula to make the calculation easy, simple, and calculate them fast. Understood? Or is there any doubt? So problem on addition theorem. A die is thrown once. What is the probability of getting a multiple of 2 or 3? See the question here. In previous classes, the problems are like what is the probability of getting a multiple of 2? And second question, what is the probability of getting multiple of 3? And now the question is only one question, getting the multiple of 2 or 3. That is multiple of 2 or multiple of 3. So when we throw a die, what is exhaustive cases here? So what is sample space? So just for this example, I'll write sample space. S is equal to 1, 2, 3, 4, 5, 6. So just now I have taken the same example. Okay, sample space 1 to 6. So what is the question now? Multiple of 2 or multiple of 3. Okay, so multiple of 2. Multiple of 2 is equal to 2, 4, 6. And multiple of 3 is equal to 3, 6. Now the question is probability of getting multiple of 2 or multiple of 3. So P of A, let event A be multiple of 2 and event B be multiple of 3. Now probability of getting A or B is equal to P of A plus P of B minus. So here both cases are not mutually exclusive. Therefore P of A intersection B. This you can write like P of A into B also, or even A and B. Or means union or addition, and means intersection or multiplication. Okay, remember that. So here we'll take intersection of B. So in intersection of A, B, intersection of A and B, what are the common cases here? So A intersection B is equal to, the common factor between both is a 6, so write 6 here. So A intersection B is only one cases is there, and here 2 and here 3. So probability of getting multiple of 2 or 3 is equal to P of A is 3, exhaustive cases are 6, so 3 by 6 plus probability of B is 2 divided by 6 minus A intersection B is 1 divided by 6, that is 3 plus 2 5, 5 minus 1 is 4 by 6, which is common here. If you draw it the same with the N diagram, okay, so N diagram, event A and event B. This is A union B. And how many are there in event A? 2, 4, 6, and in event B 3 and 6. So 6 is the common between both here, and in sample space remaining, where we have to write them? Write them anywhere in this box outside these two circles, so to show sample space or universal set. So here 1, 2, 3, 4, 5, 6. So event A 2, 4, 6, event B 3, 6. So 6 is a common here. So here 1, 2, 3, 4. That is these shows A intersection B. Both circle together A union B. Only this part 6 is A intersection B. Got it? Problem. A card is drawn from a pack of 52 playing cards. One card is drawn from pack of 52 cards. Okay. So what is the probability that it is a club or a king? So probability of club or king. So club, how many clubs are there in a playing cards? So out of 52 cards, clubs are 13. And how many kings are there in 52 playing cards? So out of 52 playing cards, kings are 4. Now what is the question here? Either club or king. Probability of club or king. Now tell me, is there anything which is common between club and king? So club has 13 cards. Out of these 13 cards, one card is king. And out of 4 king cards, one card belongs to club. That means one common thing is there here. So probability of, let A, so instead of, okay, let write it A only. Let A be getting club and let B be getting king. Okay. Now favorable cases. Favorable cases, that is n of event A is equal to 13. Okay. Now favorable cases. Favorable cases to event B, that is king, is 4. Okay. So now what is common thing here? Club and king, not club or king. Okay. So favorable cases to club and king both is 1. One card which is both club and king. Okay. So probability of getting either club or king is equal to P of A plus P of B minus P of AB. Okay, so that is P of A is 13 divided by 52 plus P of B is 4. 4 divided by 52 plus both club and king, that is 1 divided by 52. Okay, so now 13 plus 4, 17. 17 minus 1 is 16 divided by 52. 16 divided by 52 is the probability of getting either club or king. In a town, 15% of the population read newspaper A. So 15%. 15% of population reads newspaper A. And of the population, 13% of the population read newspaper B. So 13% population read newspaper B. And next point is 8% of the population read newspapers both A and B. That means A newspaper is read by 15% of the population. B newspaper is read by 13% of the population. And 8% population reads both A and B newspaper, both newspaper. So here, let A be a probability of or event of reading or population of reading a newspaper. So P of A, 15%. Here it is not a number. The figure is given in percentage. That means here it is a purely probability. So probability of A is 15%, means 0.15. So P of A is given directly here. That is 15% is equal to 0.15. And probability of B B newspaper readers is 13%. That is equal to 0.13. And P of A intersection B, A and B, those who read both A and B newspaper are P of AB is equal to 8% or 0.08. Now question is, what is the probability that a person selected at random, what is the probability that a person selected at random shall read either paper A or paper B? So probability of either paper A or paper B. If we select one person at random in the population, so probability of he may be the person who read any of these newspapers. So that is P of A union B is equal to. So here already we know that 8% population read both. So it is not a mutually exclusive here. So P of A union B is equal to P of A plus P of B minus P of A intersection B. So that is P of A is 0.15 plus P of B is 0.13 minus P of A intersection B is 0.08. Or else if you want to show the answer in percentage, you can write 15 plus 13 minus 8 in any form. Okay, so 15 plus 13, 28, 28 minus 8, that is 20%. 20% or 0.2. So 20% of the people. So probability of here they are asked probability. Okay, so probability means we have to show the answer in decimal. 1%. This percentage means out of 100 people. Okay, so out of 100 people, 20% people will read Okay, so here they asked probability. So probability of a person, selecting a person who read either A or B newspaper is 0.2. If the answer is asked in percentage, then 20%.